Okay, let's get started. Happy Monday. Come back. Class. Let's set the stage for today. So we already talked about latch. We had a memory element that was kind of triggered with level. That was not good. Wanted edge trigger. So that's why we moved from latch to flip-flop. Flip-flop is great. So you can have lots of application. But we need to know how we can design in a systematic way a sequential logic system. That's something that we want to start today. But before talking about that, we need to introduce another type of flip-flop that called T flip-flop, toggled flip-flop. That just toggle the value of the flip-flop every time we put coming, like the one coming. We're going to see that. Also, we're going to see how we can use flip-flops in Verilog for your lab. So we can talk about that a little bit. It's very easy. And then we're going to go for design. How we can design a circuit with memory. How we can design a circuit that has some flip-flop inside. We're also going to introduce state machine, a diagram that you can see in a system how a state can change. We can visualize that with a state diagram. We can talk about that too. It's a little, we are moving a little forward, more advanced circuits. We're not going to go deep in sequential circuit design. We're just going to do one simple example. But later on, we can go more and see more advanced circuits. Okay, let's start with T flip-flop. T flip-flop is another type of flip-flop that can create it from a JK flip-flop. If you remember last class, we had a flip-flop called JK. JK is actually coming from the name of the guy that invented that. That's right. So the JK flip-flop was the last flip-flop that we introduced. So it was good because it doesn't have any forbidden state, doesn't have any invalid state. So if 0, 0 coming, actually, if JK, for example, JK is 0, 0, if the Q, whatever was inside, the output is also same. When I put plus here, it means the next state. If the state is Q, the next state is still same. Or maybe I write differently. Said, yeah. Anyway, you understand what I'm saying. So if this is memory, maybe right now just write memory. Okay. So if 0, 0 is memory, if it's 0, 1, J act like a set. So it's set. If 1, 0 is reset, and if it's 1, 1, it's not invalid anymore. It's toggle. So it means if it was Q inside, it's going to toggle to Q bar. So this type of flip-flop is very advanced flip-flop. It can do so many things. But we had that last class. We want to make T flip-flop from that. T flip-flop is similar to D flip-flop in terms of simplicity. But to make that, you just need to actually connect J and K together. So if you connect J and K together, with that T, this JK flip-flop becomes T flip-flop. So T flip-flop is memory or toggle. So if T is 1, it's toggle, and if T is 0, it's act like memory. Okay, so if T is 0 is memory, and if T is 1, it toggle whatever what is happening. Why is acting like that? Because if it becomes 1, what's happening? 1, 1. And what was the state of 1, 1? Toggle. That's why we don't have these two states anymore. Why? Because we connected these two together. When we connect them together, they cannot be different. They are all same. So we just have two states, 0 or 1. 0 for memory and 1 for toggle. So this type of flip-flop called T flip-flop. It's very easy, but it has lots of applications. It has lots of applications. Like one of the applications is, for example, if this is T flip-flop. If you put input T, for example, 1, and when clock coming, they all have clock, remember? If the clock coming, every time that clock coming, so this Q get toggled. So if it was, for example, 0 first, change the color. It was 0 first, becomes 1. And then after 1 clock becomes 0. Not 1 clock, I think, from this to this. And then this. So if the frequency of this clock was F, for example, frequency of this output is going to be F2. So what we did, we are shifting frequencies. We are actually kind of slowing down frequency with T flip-flop. We can do with JK flip-flop too. We can do with D flip-flop as well. We can see them. That's something that we also want to talk today. Okay, that's T flip-flop. So the T flip-flop normally is a JK flip-flop when you connect J and K together. That's it. So with connecting these two together, you remove two states, set and reset. We don't need set and reset in that flip-flop. Okay, let's clean it up. We don't have any questions. Do you have any question about this so far? So good? Okay. So let's clean this up. What else we can say about T flip-flop? Yeah, this is what I explained. And oh, that's good point. So the T flip-flop actually lies as an X OR. This is XOR. Do you remember the Boolean expression for XOR? Do you remember that? What was the expression for XOR? A bar B plus A bar B plus A B bar. This is XOR. Okay, in this expression, so if you XOR something like A with 1, what's going to happen? Put B1. If you put B1, this is 1, so this is 0. This is going to go, so this is going to be A bar. And if you put 0, so it's toggle. If you, and if you put 0, it's going to be same. So XOR is acting like memory or toggle. So that's why if you want to see how T flip-flop acting, you can just XOR T with the current Q. That's important. This is coming from that expression. So XOR is acting like toggle. Okay, so this was good. So let's see what else we have about that. Output toggle, so that we, oh, this is the truth table. So the truth table for flip-flop showing input, memory, and the next step of memory when those inputs coming. So that's why we have always QT or QT plus QT plus 1. Or sometimes we just put Q and Q 1 plus in top. Like sometimes just put Q here and Q plus is the same. It means next step. Or next state, doesn't matter. So we are saying if the state was, if 0 was here and the clock coming, if the T be 0, if T be 0, the next step gonna stay 0. This is what we want to talk. So it means 0 act like a memory. So if this is 0, as you can see, this is exactly memory. And when it's 1, it's toggled. That's a TP. So application for counters, you can use that. For frequency division, we already saw frequency division. And counters and frequency division are very close. I'm going to explain why. And simply also you can toggle controlled logic anytime you want. So why counters and frequency divisions are very close? Imagine we have a clock like that. And then we divide the clock to this. And to this. We just divided clock every time by 2. We made it slower and slower. So right now, let's see what numbers they are creating. Okay, so this number is 1, 1, 1. This number is 0, 1, 1, 1, 0, 1. Okay, 0, 0, 1. 1, 1, 0. 0, 1, 0. 0, 0, and 0, 0, 0. Your number 0, 1, 2, 3, 4, 8. Interesting, yes? That's why we can make counter just with, so this is 0, 1, 2, 3, 4, 5, 6, 7. We made the counter just using actually multiple flip-flop that cascade after each other and divide the clock every time. And we just get output. But this is another application of D flip-flop. Also, we can see in D flip-flop you can do that as well. But I just wanted to make you ready for those things. How we can make counter using frequency division. Okay, so in Verilog, how we can work with flip-flops in Verilog. So in Verilog, we have a module. So you can define a module, and inside the module, you can have a always block part, and have some inputs and some outputs, and you can define clock. So you have everything. So you can make, for example, a D flip-flop. How? Because D flip-flop has input D, has clock, H trigger clock, and output Q. Okay, so you need to have input clock, data input, and output. And you have also always block that can be triggered with clock. So you just need to define it. Let I clean this up. So we define a module called D flip-flop. This module has two wired input, clock and D, and the output Q. And in always, we consider clock as an edge trigger. Edge trigger. So, and updating Q is because D flip-flop is so simple, we just update Q on rising edge. That's it for making other flip-flops. Also, if you know the operations, you can make it like that. This is not it's not complicated. You might use that in the lab, or you already did it last week, or you have it this week, maybe this week. Okay, that's how you use flip-flop in Verilog. Okay, but let's see more deeper frequency division. Okay, we already know frequency division happened. The reason that frequency division happened because we are edge triggered. We are edge triggered. That's the reason. Whatever is in Q, whatever is in its input, for example, D, for example, go out whatever was inside, go out, then the clock coming. Other than that, it's not going out. Nothing gonna go out. So if we put 1 here, this 1 not gonna go out till receiving the next clock. So it's already delaying. It's a kind of memory that always delay. That's what called delay flip-flop. Also, some people call it data flip-flop and delay flip-flop. It has 2 names. So it delay whatever was inside. It's gonna stay till the next step coming. So imagine that we also have a Q bar. We get a feedback. Let's get feedback from here and connect it to this. So what's gonna be the output? Look at that. So we don't have D anymore. Let's connect this to D. So if the Q was inside, for example, it was 0 or 1, doesn't matter. Imagine it was 0. The next clock coming, it's gonna be 1. And stay this time. Maybe I write this under that. Like this. So it's gonna be like that, and then like that, and like that. We already did. So this was, if the clock was like that, the new clock gonna already get delayed. So this is dividing by 2, just one with D flip-flop. But because D flip-flop is not toggling, to do that, we need to get from Q bar and get a feedback loop from D bar to D, from Q bar to D. That's it. So this is actually making a divider, divide by 2. If you want to make it divide by 4, you need to cascade 2. If you want to divide by 8, you need to cascade 3, and so forth. And if you do cascading, you also can make counter, as we explained. Okay, let's clean this up. We have a better picture of that. So when Q bar output is fed back into the D, it's gonna, for JK also we can do that. Okay, let's see for JK. For JK flip-flop, you have J and K, and Q and Q bar. And of course clock. And the clock is like that, for example. Okay. So if you want to toggle in JK flip-flop, we need to get 1. Both input need to get 1 to do toggle. And we want to do toggle, so we make this 1. Now that is 1. Every time that clock coming is toggling. So let's see what's happening. Clock coming in this. So whatever was inside, for example, 0, is toggling. And stay till the next one. Toggling again, and so forth. Is already divided by 2. If the frequency here is F, here is F over 2. So that's called frequency divider. Frequency divider, as I mentioned, has lots of application, like a counter. Okay, I ask you now, what numbers this binary, this clocks creating? Is 2. What numbers they create? Is 2 creating 1 1 0 1 1 0 0 0, counting from 1 to 3, 0 to 3. This is 0 0 0 1 0 1. This is least significant bit. This is most significant. This is 0 1 2 1 1 3. should write it to mix it up. 3, 2. Nice. But designing sequential sequence is not as simple as this. We need to go for kernel map and in a systematic way. Even in systematic way, today we're gonna create a counter like this, but without using this method. Well, we're gonna use a systematic way to teach how to learn how we can design any kind of sequence. Okay, that's frequency division. Let's clean this up. This for JK flip-flop. So for JK flip-flop, we just need to connect it to 1 or high. What about T flip-flop? What about T flip-flop? I already told you. For T flip-flop is also, because T flip-flop is JK and K is already connected, so we just connect T to 1. And when the clock coming, it's already toggling. This is T flip-flop. Easy, just similar to JK. Just connect it to 1 or high voltage. Okay, that's it. That's frequency division. So you can cascade more than one. We're gonna see the next slide. To divide by 4 or 8 or 16 or 2 power n. If you cascade log of to you can see that. Okay, cascading flip-flop for frequency division. We already explained this. So here you can see 2 flip-flops cascaded. The first one get from clock. The next one get from the output of the first one. So here, so the QB, this is the numbers that created. Like this is this significant bit. Yeah. Oh yeah. And most significant bit. So we already explained this. We can go to any question about this? You're gonna see similar if you examine your assignment. Please. So if you have anything that is not clear, just ask me. It's not difficult, but you need to have some background from before to understand them. Like at least you need to know this flip-flop, how it works. So, however, it's very easy. This flip-flop is the easiest flip-flop because whatever is coming input is going output. Then the clock coming. It's just delaying the input. How much? 1 clock. And that's why it's called delayed flip-flop and later. So generally, if you want to have, if you have n flip-flop, you can make a counter. You can divide the clock by 2 power n. Like here, for example, we have 2 flip-flop. We divided by 1 over 2 power 2 is 1 over 4. This is 1 over 2, and this is 1 over 4. Okay, counting, as I explained, counters and frequency division for dividers are very similar. I mean, they do the same job, actually. The reason is that, for example, here you are kind of this J flip-flop that we cascaded 2 J flip-flop, and we create one divide by 2. This is a divided by 2. Whatever is here, frequency here, this frequency is divided by 2. Here is divided by 4. And as you can see, the numbers created, we didn't consider clock here, but we can consider that as well. But without that, we created 0, 0, 1, 0, 0, 1, and 1, 1. 1, 0, 1, 2, 3, and it's repeating. That's called counter. Counter is repeating. Based on the number of bits, 2 bits between 0 to 3, and from 0 to 3 and repeating and counting. So as you can see, using 2 flip-flop JK, we cascaded them to make these numbers. Okay? And counters are essential for timing, for counting, for digital control, and so many applications. We're going to design a counter in a systematic way as well. But this is not a systematic way. This is just a general way that you can use with cascading. It's not a systematic way. We can see. Okay, we want to now go for systematic way to design a sequential circuit. That's the important part. We want to see how we can design a circuit when we know the states. States are important. We need to know states, and we need to know how a state's changing. And we also need to know what is the type of sequential circuits you want to use. If you remember, we had 2 types of sequential circuits, Moore and Mealy. In Moore, the output actually is just a function of the previous states. So this is the diagram that we had that before. So we have some combinational logic. We always have combinational logic. We just add some memory to the system. So we have combinational logic. We have memory. We might have another part just do some other jobs and make output for us. Or maybe this is just the output. So, but the output is from flip-flop or from the memory part. So it means what? It means output is triggered by clock. The output is ready when the clock comes. So the output, it depends on clock. So it makes more machines actually more stable. It makes this machine more stable because it's triggered by clock. Clock is working like a stabilized circuit all the time. Why stabilized? Because it's not changing between. The clock makes it synchronized. So that's a characteristic of Moore machine. But Moore machine is very easy, at least easier than the Lee machine. In Lee, the output, it depends on not just memory, but from the input too. So that was the design that we had before. So as you can see, we have memory. We have some combinational logic. Actually, this 2 combinational logic can be just 1 part, but we put it in 2 parts to show. And we have some inputs. And the output is not going from flip-flop. So it means it's not triggered by clock. The output is not triggered by clock. Anytime input changing, make decision. The output gets ready. So that's characteristic of Mealy machine. Question? Okay, so the Mealy machine is like that. It's more complex. we're going to see the application later. So the state machine, a state diagram, in addition to state, you also have input. Like this is for actually for that example that we had before, bottle return, like a vending machine. This is for that. We can solve that when I explain the method, but generally, the reason that I put here, I wanted to show you when you are moving from one state to other state, the input need to come to make that transition. The input is important to this transition happening. So if we are in a state 25 and 25 cents not coming, this is when the user enter money to get, for example, water or drink. So enter 25 cents. It can continue sending 25 cents, or it can send 50 cents and $1, for example. So this is modeling that. And first, bottle need to be in a place. If it's not repeating, if it's there, it's going there at state 1, state 25. In the state 25, if the 25 is coming, it's going to go back to 0, maybe get another 25. If not, maybe the user enter 50. In this case, it's going to be in this state. If get 50, again, going to go to 0, maybe get another 50 or 25, or go to $1 and do another. And as you can see, transition between the states, the main transition happening when the input coming. So this actually is very advanced circuit. But we can see that later. But today we're not going to go that advanced. We're going to design very simple circuits. But what is the steps? What is the design flow? The steps start with problem definition. You just need to define the problem properly. Like if you want to design something, you need to describe it very nicely to see what is the input, what is the output, what system doing. And most of the time, if the system is sequential, you need to design the state diagram. You need to be able to design the state diagram. Because these systems have memory, and memories are those states. And I explain what is a state. States are just the numbers that summarize the condition of the system. The minimum numbers, the minimum number of actually values. So if, for example, you want to design a counter between, example, you want to design a counter, this counter is going to do the same things that what we did before, but different circuit, because this is systematic ways, is not same as that at the end, but they do the same things. So we want to do a counter, count from 1 to, for example, 4. So we have, how many states we have? 4 states. A state 0, for example, state 1, state 2, and state 3, for example. We have 4 states. And the state 0 is for 0, state 1 is for 1, 2, and 3. So state 0, going to a state 1. This direction of transition is important. Okay, this is a direct graph or directed graph. 3, and come back to a state 0. This is called a state diagram. That's showing how state's changing. Because we need to know in each clock, when the clock coming, we are transferring from one state to the other one. So the input for transition is clock. Okay? So that's the second step, draw a state diagram based off Moore or Mealy. And assign binary code. We also assign binary codes too. If we have, for example, 4 states, we can use 2 binary digits to actually model that. If we have, for example, 10, imagine we have 10 states. How many binary digits we need? 4, exactly. We need to have, we learned this before. So the n is 4. Because 3 is not enough. 3 is still 8, but it's not enough. So we need to consider 1 more. Okay, so assign binary code. So we did already. And then we build a state transition table. We build a state transition table. A state transition table showing what is the state before and the next state. Like for example here, if the state is 0, 0, 0, 1, 1, 0, 1, 1, the next state gonna be 0, 1, 1, 0, 1, 1, 0, 0. So this is for example, Q0 and Q1. This is Q0 plus and Q1 plus. I ask you now, how many flip-flops we need to design this circuit? How many? Can we use 1? 1? Okay.
Because then one of them is
no, yeah, the systematic way is not using clock as an output. In a systematic way, we are not using clock as a, the part of the answer. Yes. In systematic way, yes. Any other answer for that? 2, 4, 1, 2. Why 2? Because we have 2 bits. I already mentioned Q0 and Q1. So we need 2 flip-flop because we have 2 bits. So from the binary code, when we assign the binary code, we also can understand how many flip-flop we need based off the binary code. For that example that I mentioned, we have 10 states. We need 4 flip-flops. So that's the important part. So we need 2 flip-flop because we have 2 digital bits to store, Q0 and Q1. So that's a transition. Okay, transition is not as easy as this, but if you want to design with D flip-flop, the simplest one is like as easy as this, because in D flip-flop, input and output are equal. So we just easily can change Q to D. And drive the next state and output equations that here is that table showing all of them, and then implement with flip-flop. So here, for example, you can do that. But first we need to find the relationship between these two. Okay, so as you can see here, that's the output part. So the Q1 plus is Q1 bar 0 plus Q1 bar. Q1 x over Q0. You can design with, if it's just two variables, it's so easy. You don't need kernel map. But if it's too much, we can design kernel map too. And what about Q0 plus? These two is Q1 bar Q0 bar plus Q1 Q0 bar. That this can easily get Q0 bar because Q1 gonna remove. So we found relationship between the next state and previous state. What is the next? Let's see. Let's clean this. Oh, okay. I have this in the next slide too. So, and then we implement the flip-flop. So we're gonna see that this is the state machine that you already designed. We, in a step one, we define the problem, and then we define the counter, how it's counting. And because we have two numbers, digital numbers, we need two flip-flops, Q1 and Q0. And we define the state machine for a state diagram. And then this is the table that I already mentioned. This is a state, and this is next state. And find D1 and D0 that you already did. And the rest is just designing that. You have two flip-flop, D0 and D1. That because it's D flip-flop, D0 is already Q0. They are equal. So clock is connecting to both. For D1, we are exporting Q0 and Q1. Make the new one, D1. For D0, we have already Q0 bar and connect. And this gonna make exact counters that we did in a different way. This cascading flip-flops. We can test that too. If you test it, if you start going clock, you can see that it's going to generate 0, 0, 0, 1. But this is not time. But next class, we can go more advanced and see how. But that's a general way. So you learn how you can systematically design a sequential circuits. So next class, we can see more examples. Don't worry. But go deeper and start working on that to understand.